Hi, today in this video I will be discussing and analyzing the motion of a peanut butter jar and comparing this motion to the expected outcomes using Newton's second law. The purpose of this lab is to put Newton's second law into perspective and see how reliable it is for predicting motion in the real world. Newton's second law is as follows. It is the final velocity is equal to the initial velocity plus the net force over the mass of the system times the delta T. For this lab, we are assuming the net force on the jar to be equal to 0. Therefore, the net force over the mass times delta T should be equal to 0, and the final velocity will be equal to the initial velocity at all times. We should see a constant velocity throughout the lab. The peanut butter jar has a mass of 0.28 kilograms, and the lid of the jar is 0.075 meters in diameter, which is what I used to calibrate my system. I had it rolling across a carpeted floor. Now let's put Newton's second law to the test. For analyzing the motion of the jar, I flipped the x-axis so that the jar is actually rolling in the positive x direction instead of the negative x direction, so that the results would make more sense to people viewing the results of my lab. I also tilted the axes a little bit to make sure the x ran parallel to the motion of the jar. I also chose the time span of the video when the jar had fully accelerated so that the velocity would be constant throughout the parts of the video that I am analyzing. As you can see, the results are pretty consistent, leading to a linear graph of the jar's position over time, or a constant velocity. However, there are a few human errors, such as the jar moving towards the screen and not placing the point mass trackers in the center of the cap each time on the jar. In order to see what Newton's second law would have predicted without errors and no net force, we can use a model made in Python. In order to see what Newton's second law would have predicted without errors and no net force, we can use a model made in Python. This is the Python code I use to make my model. To start, I input the initial position vector given in Tracker and the initial velocity vector. I also put in the ball's mass, which is 0.28 kilograms, and here's the initial position, which is 0.006 in the x direction, positive x direction, 0 and 0. In order to calculate the initial velocity vector, I had to use the first two position points given to me through my analysis in Tracker. The equation I used is the velocity is equal to the second x position minus the first x position over the change in time. This was equal to 0.02 in the positive x direction minus the initial 0.006 in the positive x direction over delta t, which was 0.033 seconds. And this gave me an answer of 0.424 meters per second. And that is what I put in Python as my initial velocity vector. I also put that the initial time, was equal to 0. I also had my delta t equal to 0.033 seconds, which is the same delta t used in the Tracker analysis. I also clarified that the net force was 0, or the vector of 0, 0, 0 in the x, y, and z directions. Then I had to put in Newton's second law equation that the final velocity is equal to the initial velocity plus the F net over the mass times delta t. As you can see, this graph looks very similar to the graph I have on Tracker already. Now, let's compare these predicted results with the observed results in the experiment. Here on this side, we have the predicted time and the predicted position, and on this side, we have the observed times and the observed positions from the results that I found in Tracker. The red line is represented by the predicted position, and the purple line is represented by the observed position. As you can see, Newton's second law is definitely a reliable equation to use for the prediction of motion of an object with no net force. In the beginning, the results are pretty precisely matched with the predicted results from the model. Over time, however, the observed results become a lower velocity than expected. But this is because of forces such as friction and air resistance that cause the velocity of the jar to decrease slightly. Also, you can see that the predicted position, or the positions given to me through Python, my Python model, have a consistent velocity, which means that my Python model worked as expected. Overall, Newton's second law is applicable to many objects in motion in the real world, and I could have shown that better if I had a way to have absolutely zero net force. Hopefully this gives you a clear view of what Newton's second law is and how it applies to the real world.